Today we're going to be talking about vectors in a coordinate plane. So far we've looked at vectors independent of a coordinate plane. We've drawn them on a horizontal and vertical axis, but we haven't thought of them on the coordinate plane yet. The way we write vectors, we know that all vectors have an initial and a terminal point, but we write them in what's called component form, where it's x comma y. And notice we do the brackets kind of like less than greater than symbols. X is actually the distance from the initial point to the terminal point on the x-axis, and the y component is the distance from the initial point to vertical or terminal point on the y-axis. And we denote this as, if we talked about initial terminal point, OP, we denote it with this little line. It's like half of an arrow on it, and so that symbolizes vector. So what we can do is we can find the component form of a vector if we know our initial point x1, y1 and our terminal point x2, y2. And essentially all we do is we find the difference between x2 and x1 and the difference between y2 and y1. And that's how we write it in component form. So if I look at example 1 here, it says express or find the component of vector AB with initial point -4, 2 and terminal point 3, -5. So AB, my vector, is going to be this then. Okay? So if I say this is x1, y1, and this is x2, y2, x2 minus x1, comma, y2 minus y1. Well, 3 minus a -4 is 7. And -5 minus 2 is -7. So here is my component form of vector AB. You can try the same with the guided practice A and B. Now, how do we find the magnitude of it? Well, we use the same points again. Initial point x1, y1, terminal point x2, y2, and we find it essentially using the distance formula between them. And remember, magnitude of ours is written in what looks like the absolute value symbol. Okay, so if we know component AB, it's going to be the square root of a squared plus b squared. So let's look at example 2. It says find the magnitude with an initial point of -4, 2 and a terminal point of 3, -5. So my magnitude B is going to be, remember, x1, y1, x2, y2. So x2 minus x1 squared plus y2 minus y1 squared. Simplify it to be 7 squared plus -7 squared, which would be the square root of 98. So that is going to be my, I guess if we reduce that down, approximately 9.9. So that's my magnitude right there, 9.9. If I wanted to check, notice these points are the exact same from example 1. So we know our component form is 7, -7. So if I wanted to check, remember it's just a squared plus b squared. Notice that is the same as this. And so again, I get the square root of 98. Which is 9.9. So we know that we did it right. Here's some more guided practice problems. Feel free to try these with A and B. Now, vector operations. Now this is pretty cool about vectors. What we can do is, when we have vector A with components A1, A2, and vector B with components B1, B2, if I'm going to add my vectors, all I do is simply add the x components and add the y components. Vector subtraction, same thing. Subtract the x components, subtract the y components. And when I have scalar multiplication, meaning I'm taking some value x, or k, and multiplying it by my vector, all I'm doing is just multiplying it by both components x and y, or a1 and a2. So it says find the following for w being the vector with components -4, 1, y being the vector with components 2, 5, and z being the vector with components negative 3, 0. I'm looking for w plus y. Well, w plus y is going to just be adding negative 4 is my x component for w, and 2 is my x component for y. And then I'm going to add 1, the y component of w, and 5, the y component of y. So then that would be negative 2. There's my answer. Now letter B, z minus 2y. So first I need to find what 2y is, right? So that's 2 times the components 2 and 5. So really, 2 times 2 is 4, and 2 times 5 is 10. So this is what 2y is right here. And so now I can take z minus that. So z minus 2y is going to be negative 3 minus 4, and then 0 minus 10. So I simplify. Negative 3 minus 4 is negative 7. 0 minus 10 is negative 10. There's 3 examples for guided practice if you'd like to try them as well. The last thing we're going to talk about today is what's called a unit vector. And unit vector is when you have some magnitude of 1. Okay? So instead of having a full magnitude, a full distance, what we're going to do is just want it to have 1. And so the way we figure that out is, say we have some vector, unit vector u, and we want it to have the same direction as v. So what we have to do is we have to take v and divide it by the magnitude of v to find out our unit vector. Okay? It's kind of like dividing down so that you have something over 1 as a fraction. So if we want to look at this one, it says find the unit vector u with the same direction as a vector v with components negative 2 and negative 3. Well, the equation we just looked at is this, right? 1 over magnitude of v times the components of v, which in our case would be negative 2, 3. So we need to figure out this magnitude right here. So we look back and we say, okay, well, how do we find magnitude when we know components? Remember, that's just x squared plus y squared. So that'd be negative 2 squared plus 3 squared times negative 2, 3. Well, negative 2 squared is 4. 3 squared is 9. So this would be 1 over the square root of 13 times negative 2, 3. Now remember, we don't like to have square roots in the bottom. So how do I get rid of the square root on the bottom? And multiply it by the square root of 13 on both top and bottom. So now we have the square root of 13 over 13 times the components, negative 2, 3. And so we said scalar multiplication is I'd just take this amount right here, the whole thing, and multiply it by negative 2 and by 3. So it'd be negative 2 square roots of 13 over 13 and 3 square roots of 13 over 13. So if I had components negative 2, 3, and I wanted it to have a unit vector, meaning a magnitude of just 1, this would be my components now with the same direction as my original vector, just with a magnitude of 1.